Hello teachers, welcome back to Chapter 6, Section 6-3, where we're talking about multiplication and division of rational numbers. And I'm starting off with an example. Don't usually do that, that's just the way the video is stacked up. We have 35.5 yards of material available to make towels. Each towel requires 3/8 yards of material. How many towels can be made? So process that for a minute. What should we do? Well, we've got a 35.5 yards and it takes 3/8 for each one. So let's split that 35.5. Let's split it up into 3/8 yards pieces, right? Notice the units are the same for both of them. So you don't have to do any kind of conversion or anything. We just need to do the math right here. So how do you want to do it? My suggestion is to take that 35.5 and change it to an improper fraction. So remember what you can do. You have 35 times 2, add 1, or the option is you can write it as 35 plus 1/2 and find a common denominator for 35 over 1 and 1/2 and then add them together. Either way works. This way, where you do 35 times 2, which is 70 plus 1 is 71/2, is just a little bit faster, divided by 3/8. Now, the next thing is, how do you divide fractions? If you'll recall, keep, change, flip, right? You keep the 71 over 2, you change division to multiplication, and you multiply by the reciprocal of your divisor, which would be 8/3. Now, if you like, you can simplify before you multiply. Remember, we can divide both this numerator of 8 and this denominator of 2 by the greatest common divisor of those two, which is 2. So 2 divides into 8 4 times, 2 divides into 2 1 time. And then you can multiply 71 times 4. And by the way, does 3 divide into 71? I really should check that, right? We know very quickly that 3 doesn't divide into 71 because 7 plus 1 is 8, and 3 doesn't divide 8. So 4 times 71 is 284, and then 1 times 3 is 3. But we really can't tell how big that is until we change that to a mixed number. So I'm going to come down here below. I'm going to divide 3 into 284. 3 goes into 28. Remember, 3 times 7, 3 times 8, 3 times 9 is 27. So let's say 3 times 9. Bring down my 27. I subtract. 28 minus 27 is 1. Bring down that 4. 3 divides 14. 4 times 3 is 12. Subtract and get a remainder of 2. So this is equivalent to 94 2/3. Remember, quotient plus remainder over divisor. All right, now, how many towels can be made? 94 2/3. What do you think about the 2/3? Well, we don't need 2/3 of a towel, so how about 94 towels? That answers the first question. Now let's check out the typed up version of that result. So notice that we've got 94 this time too. We took 34.5 divided by 38. Notice it was changed to 71/2. That's exactly what we did. Times, again, you multiply by the reciprocal whenever you're dividing. Get 284 over 3, which reduces to 94 2/3. So 94 towels can be made. But there's another part to this question. Part B, how much material will be left over? Now, your first thought, you're thinking 2/3 would be left over. Is that right? Let's go back and look at our result. We've got 94 2/3 towels. Not 2/3 of a yard of material. That's 2/3 of a towel left over. All right, so let's write that down. You want to? So 2/3 of a towel is left over. Now, how big was the towel? Do you remember? We could go back and look, can't we? So 3/8 of a yard. Each towel requires 3/8 of a yard. So if there's 2/3 of a towel left, then wouldn't we multiply? That's 2/3 of means multiply. A towel is 3/8 of a yard. If we multiply that together, the 3's cancel out. Not only that, they both divide by 3, right? 2 and 8 both divide by 2, so 2 divided by 2 is 1, 8 divided by 2 is 4, and we multiply 1 times 1 is 1, and the denominator 1 times 4 is 4, so there is 1/4 or 1/4 of a yard of fabric remaining. So check out the typed up version of that. Notice that's exactly what we did. Let's try another problem. A bookstore has a shelf that is 37.5 inches long. Each book that is placed on the shelf is 1 1/4 inches thick. How many books can be placed on the shelf? So once again, we're dealing with 37.5. Not that we're dealing with 37.5 again, but once again, we're going to divide. So we got 37.5. We want to divide that by the size of each book to figure out how many books will fit on the shelf. So 37 1/2 divided by 1 1/4. Now, do we want to do division like that? Absolutely not. Let's change that once again to an improper fraction. 37.5. We say 37 times 2 plus 1. It's going to give me 75 halves divided by 1 1/4. Again, 1 times 4 is 4, plus 1 is 5/4. And we know the rule for dividing fractions. You keep the dividend, you change division to multiplication, and you multiply by the reciprocal of the divisor. So you keep, change, flip. Now it's time to multiply. I can simplify this beforehand. You know the drill. 2 and 4 have a common factor of 2. So 2 divided by 2 is 1. 4 divided by 2 is 2. 75 and 5 have a common factor as well. 75 divided by 5 is 15. And 5 divided by 5 is 1. And now when we multiply, we get 15 times 2 is 30. And then 1 times 1 is 1. And we know 30 over 1 in simplest form is just 30. 30 what? 30 books will fit on the shelf. Now, if you look at the work here, they wrote this differently. They said 37.5, and then a fraction bar, 1 1/4. Is that the same thing as what we wrote? We wrote 37.5 divided by 1 1/4. Sure, it's the same. You remember, a fraction bar really does mean division. 1 divided by 2 is the same as the fraction 1/2. 1 split up into 2 parts. 1/4 is 1 split up into 4 parts. 37.5 over 1 1/4 is 37.5 split up into 1 1/4 size pieces. And then they go on to simplify. Notice that matches the work that we did, although it looks a little different. You know why? They did not simplify beforehand. They didn't cancel the 2 and the 4 here and the 75 and the 5. Is it okay that we did? Sure it is. We still got 30 books on the shelf, right? Now let's talk about estimation and mental math with rational numbers. Estimation and mental math strategies that were developed with whole numbers can also be used with rational numbers. We did a little bit of estimation when we added and subtracted rational numbers. Well, now we're going to do it when we multiply and divide rational numbers. Check out example 22 here. It's coming, I promise. So you're trying to round each one of these before you multiply. So you've got 3 1/4 times 7 8/9. Okay, one of them I would expect to round down. 3 1/4. 1/4 is closer to 0 than it is 1, so that could be 3. 7 8/9 is actually closer to 8 than it is 7, so I'd round that to up to 8. So that could give you approximately, again, 3 1/4 round down to 3, 7 8/9 round up to 8, and that's about, I should put approximately 24. Another way to handle it is to look at a range. If you look at a range of values, the lowest it could be is if you round them both down. 3 times 7 is 21. What about the highest it could be? Round up, 3 rounded up to 4, and then 7 rounded up to 8, and that would give you 32. So a solid range of values would be between 21 and 32. So it really just depends on what you need. It just said estimate, but when you look at the typed up result, it says the product will be between 21 and 32. Why don't you try the same thing on the next problem? Come up with a range of values and pause it before you do that, and then come back and let me know. All right, how'd it go? So 24 and 5/7. Now the lowest that could possibly be is 24. Let's get the pen working again. There we go, 24 divided by 4 and 1/8. The lowest you could round would be 4. We know 24 divided by 4 is 6. On the other end, rounded up, 24 and 5/7 rounded up is 25. Divided by 4 and 1/8 rounded up, divided by 5. It happens to be that these numbers just work out nicely. 25 divided by 5 is 5. Okay? And so the range, you wouldn't say is from 6 to 5, but rather you would say a range between 5 and 6. Because it ended up backwards, right? And because we were dividing. Now if we look up at the typed up version of that, the quotient will be between 5 and 6, exactly like what we said. Now I want to spend a little bit of time on properties of exponents. In the first video opening up, I warned you that that might be the most challenging part of this section. Probably so. Properties of exponents, we got a lot of properties, so hang tight. A to the 0, remember that is 1. Now what could A be? A and B for any non-zero rational number, so think fractions now. A and B can be fractions, and M and N are integers. Okay, positive or negative. So M and N are integers. So here we go. A to the 0 is 1. We have seen that before. What about A to the negative M? Now this is the first we have seen of this. So anytime you see a negative exponent, look what happens. That belongs in the other side of the fraction bar. That's my dog. I'm sorry about the jumping around. All right, so if you have a negative exponent, that belongs in the denominator. So notice the negative M moves down to the bottom, and now it's a positive M. That is the definition of a negative exponent. All right, if you have A to the M times A to the N, remember what we did when we had integers and whole numbers? You just added those exponents. Same rule applies. What about if you're dividing? Then you subtract exponents. Again, that's an old rule also. A to the M to the N power is A to the M times N. That's also an old rule. A over B. Now this is a new one. If you have a fraction raised to a power, then that's going to be A to the M divided by B to the M. So notice the numerator and denominator are separately raised to that exponent power. What if you have a negative exponent up here? Notice what happens. If you have a negative exponent, your A over B flips to B over A, and your negative M changes to a positive M. That is a new property that we only have with fractions. And then the last property, this is an old property. If you have a product inside raised to a power, then you can raise each one of those to that power. So A to the M, B to the M. Now let's do some examples. Use properties of exponents to justify the equality or inequality. So we're supposed to use properties to show that these are not equal to each other. So you can pick which side you want to go to. All right, let's start with the definition of a negative exponent. So if I rewrite, that's going to be 1 over, come on pen, 1 over negative x to the positive 2 power. Notice all I've done is use the definition of a negative exponent. Let me go back to that for you. So you'll see that it is this one right here. I just took what we had, the base, to the power, threw it in the denominator with a 1 on top. That's all we did there, okay? What's up with the parentheses? Because that's a negative x inside, I had to keep the parentheses around it. Since it was to a negative 2, they stay. Now, what happens when you square a negative number? This is the same as saying negative x times negative x, if you need help seeing that, which gives you 1 over x squared. So a negative to the second power goes away. Now, is that equal to negative x to the negative 2? Well, let's work on it. Let's work on the left-hand side. So negative x to the negative 2 is actually, the only thing that's to the negative 2 here is the x. We've talked about this issue before. If you want parentheses around it, all of it goes to the negative 2 power. If you don't put parentheses around it, the only thing that goes to the negative 2 power is the x. So by definition, this is negative 1 over x to the positive 2. Now compare the answers. These are definitely not the same. And we have justified it. Now I've got that result typed up. Let's see if it was handled the same way. So they took x to the negative 2. They kept those parentheses, put it in the denominator. And look, the negative x to the negative 2, they worked it across like this, and that's negative 1 over x squared, which is what we got. And they point out that 1 over x squared is not the same thing as negative 1 over x squared, right? It's not. One's positive, one's negative. Therefore, the original problem is not equal. We'll try another one. So example B, we're trying to show that negative x to the negative third power is the same as negative x to the negative third. This looks just like the last one, but we changed it from 2's to 3's as exponents. Okay, so if I work with this side, the left-hand side, that gives me 1 over negative x to the third power. But we know when we raise a negative to the third, that's the same as 1 over negative x to the third power, because the negative times the negative times the negative 3 times overall is a negative, and that can be written as negative 1 over x to the third. So this is the left-hand side. Right-hand side I'm going to do in pink. So if we start with negative x to the negative 3, now I'm going to handle this part because the negative does not go with the x in this story. So this is negative 1 over x to the positive 3. There is no simplifying to be done here, but notice that they match. Okay, look at the next example. Left-hand side I'm going to do in green. A times b to the negative 1 power. Now, what's actually raised to the negative 1 power? Just the b. That's it, because there's no parentheses. So that's going to be a over b to the first power, which can be written as a over b. That's the left side completely simplified. Let's look at the right side. Now here, this whole expression a times b is raised to the negative 1. That would be 1 over ab to the first power, which could be written as 1 over ab. That's completely simplified. Notice those do not match. And here's the typed up version where we showed that negative 1 over x to the third is the same as negative 1 over x to the third. I like the way we wrote it better. And then this problem, 1 over ab is not the same as ab to the negative 1, which is ab to the negative 1 is a over b versus 1 over ab. So again, we got this result, and they do not match. I've got more. Why don't you pause it and see if you can knock these two out. Now, when you're looking at the left-hand side of example D, I'm going to handle this outside exponent first, and that applies to everything in parentheses. So the first thing I'm going to do is write 1 over, and then in parentheses I have a to the negative 2, b to the negative 2, and now that's to the positive 1 power. I'm going to keep working to the right. Now when you have something to the positive 1 power, it really doesn't change the values. You could say negative 2 times 1 is negative 2, and negative 2 times 1 is negative 2, which would result in a to the negative 2, b to the negative 2. But now remember the definition of a negative exponent. What that really means is this belongs on the other side of the fraction bar, so does this one, and it changes the exponents to positive. So this is a to the second, b to the second. What stays in the bottom, there's a 1 there, which is just a to the second, b to the second. And look at there, that's exactly what they wanted us to compare it to. I don't even have to do anything to the right-hand side. All right, next example. Again, I'm going to start with the left-hand side. That looks to be the most complicated for sure. So this negative 1 on the outside, that's what I'm handling first. All of that in parentheses, and now is a denominator. So this is a to the negative 2 plus b to the negative 2, and there's a 1 there. All right, now notice what we're comparing it to has a positive 2 exponent. So the next thing that I would need to do is handle this negative 2 exponent. Does that mean it just goes to the top? It doesn't, because this is addition. You can't just take all of that to the top. These are separate. So this is where this one gets weird. I have to write a to the negative 2 as 1 over a squared, plus this is going to be 1 over b squared. Those are separate fractions. To be able to simplify this, I would have to add these together, but I can't because they don't have a common denominator. So I could build one by multiplying my first fraction by b squared over b squared, and my second fraction by a squared over a squared. Now that's going to give me a 1 still in the numerator. This is going to give me b squared plus a squared over my denominator, which I could write as a squared b squared. Now we can, you're going to love this, we could keep, change, flip. So I'm going to keep my numerator as 1. I could write it as 1 over 1. I'm going to change my division, notice the dot, multiplication, and then I could write this as a squared, b squared over b squared plus a squared, or you could write it as a squared, b squared. Remember, the order we add in doesn't matter, a squared plus b squared. Now, can I cancel these a squareds? Absolutely not. You can't cancel part of a sum. Same thing with the b squared. Y'all, that's as simple as that gets. But it is definitely not the other side. So we showed that this is not equal to what we have down here in the denominator. They get a little bit more complicated, don't they? Okay. Again, let's look at the typed up version. So just so you can see, we did show the first one, a squared, b squared. Oh, look how they, oh, I didn't flip it. How they handled E. Look, they did exactly what we did, okay? But in a different order. They wrote the inside first as 1 over a squared plus 1 over b squared. Then they added them together. And then they handled the outside exponent. But notice the result is the same, a squared, b squared over a squared plus b squared. And again, just as a reminder, those don't cancel. All right, now this is different. Perform the following computations and express your answers without negative exponents. All right, so we want to express our answer without negative exponents. We could do 16 squared divided by 8 to the third. Right, what I did, because of that negative exponent, I took it to the denominator. Now watch this. We're going to try to do all this without a calculator if we can. 16, I bet you agree, is 2 times 8 squared. I just rewrote 16 as 2 times 8, and in the denominator I have 8 to the third. Well, whenever you have parentheses with an exponent on the outside, as long as it's multiplication, you can write that as 2 squared times 8 squared over 8 to the third in the denominator. And I can subtract these exponents. There's 3 8s down here, and there's 2 8s up here. That's going to give me 2 to the second over 8 in the denominator. 2 squared is 4 over 8. Finally, that gives me 1/2. All without a calculator. And that's the idea, is see if we can pull this off without a calculator. So maybe stop, pause it, see if you can follow what I did there. The reason I wrote 16, again, is 2 times 8, instead of, say, 4 times 4, is because I had an 8 to a power down here, and I knew I could cancel those 8 exponents, those 8 bases with the exponents up there. Now let's try that same idea with the next one. So I have 20 to the second power divided by 2 to the fourth power. Notice I wrote it as a fraction bar instead. It's a little easier to look at that way. Now, because I have a 2 as a base down here, I could pull out a 2 as a base up here. I'm going to rewrite 20 as 2 times 10. That's to the second power, and 2 to the fourth in the denominator. In the numerator, because that's to the second power and we're multiplying, I say that's 2 to the second times 10 to the second And in the denominator, that's 2 to the 4th. Once again, I could subtract. 4 is bigger than 2, so 4 minus 2 leaves me 2 to the 2nd in the denominator and 10 to the 2nd in the numerator. Hey, we know 10 squared is 100 over 2 squared is 4, which gives me 25. You could even break down 10 as to 2 times 5, and the 2 squareds would cancel, and you would get 5 squared left, and that's the 25 I had there. But the goal is just to try to do this without a calculator. Now, the typed up versions of those, just so you can recap quickly and see it again. Here's the first one. So, they left the negative exponent. I'm always a proponent in changing your negative exponents to positive exponents because it's a little bit easier to see. But there's nothing wrong with this argument. They rewrote 16 as 2 to the 4th squared, which is 2 to the 8th. And they wrote 8 is 2 to the 3rd to the negative 3. And then look, they multiply these exponents. 4 times 2 gives me 8, and 3 times negative 3 gives me negative 9, which when you add these exponents, 8 plus a negative 9 is negative 1, which would give us 1/2. So there's more than one way to get there. Let's see how they handled the second one. So they said 20 squared divided by 2 to the 4th. They rewrote 20 squared as 2 squared times 5 times to the 2nd power. What is that really? That's 4 times 5 is 20 to the 2nd power. They put all those 2's in there because you had a 2 to the 4th in the denominator. Now 2 squared squared is 2 to the 4th. They canceled 2 to the 4th and 2 to the 4th and left 5 squared. Is that the only way to do it? Certainly not. We did it a different way, right? Right, what can we do with this next example? Well, to me, it's screaming distributive property. So I'm going to multiply this 10 to the 3rd inside to each one of these terms. I'm just going to write it. So it's going to be 10 to the negative 1 times 10 to the 3rd plus 5. I want that to be a 5. So 5 times 10 to the negative 2 times 10 to the positive 3 plus 3 times 10 to the negative 3 times 10 to the positive 3. Now what I want to do next is handle these 10s. Remember, when you multiply the same base, you add the exponent. So this is 10, negative 1 plus 3 is to the 2nd, plus 5, and then negative 2 plus 3 is 10 to the 1st. Over here, negative 3 plus 3 is 10 to the 0. Now what's 10 to the 0? That's 1. So let's write this simplified. 10 squared is 100, plus 10 to the 1st is 10 times 5 is 50, plus 10 to the 0 is 1, so 3 times 1 is 3, which gives us 153. Now let's see how that typed up. Notice it looks pretty much just like exactly what we did. We distribute the 10 to the 3rd inside, so notice it went with each one of those terms inside. Then we added exponents, so negative 1 plus 3 gives me 2, negative 2 plus 3 gives me 1, and negative 3 plus 3 gives me 10 to the 0. And again, just to recap, 10 squared is 100, plus 5 times 10 to the 1st, so that's times 10, which is 50, plus 3, 10 to the 0 is 1, and that gives us 153. Now, how could we handle the next one? So this negative 4 exponent, I could take it in now, or there's different ways to do these. I could try to handle my exponents now. So this y to the negative 2, let's take it to the denominator. So the x third stays in the numerator. The y to the negative 2 turns into y to the positive 2 in the denominator, and that's to the negative 4 power. I'm always wanting to handle negative exponents. What do we do with this negative exponent? You know what? I can flip this fraction upside down. So now it's y to the 2nd over x to the 3rd, and now it's to the positive 4 power. And then I have a power to a power. So, and this 4 can go with each one. So y squared to the 4th over x to the 3rd to the 4th. And then we simplify. Y squared to the 4th, you multiply these. That's y to the 8th. And in the denominator, you multiply 3 times 4. That's x to the 12th. So final answer, y to the 8th, x to the 12th. Let's look and see how this was simplified. We've got it right? They went ahead and applied the -4 exponent to both of these. So they said -4 times 3 is -12 exponent. -4 times -2 is +8 exponent. And then you leave the y to the 8th in the numerator because it was already positive. And the x to the -12 went to the denominator because it was negative. That's a couple of steps faster. Not always known for doing something the fastest way. I try to do it the easiest way for everyone to see. But again, I'm glad you're seeing both of these ways because they're both right. Now I've reached my 30-minute mark, so I'm going to shut this video down and come back for just a few more slides of examples of straight from the homework. So I hope you have a great day. Come back for part 3 if you need a little bit of help with the homework.